Welcome. We're going to now actually apply those things we've been talking about this last week or two. And we're going to get into RSA encryption. So, just a couple of reminders, RSA encryption, it's one of the most powerful and most common things. It was developed, RSA is the initials of the three gentlemen who came up with it. So, I'm going to review some of the mathematical principles and we're going to talk about how we actually execute RSA. So, the first thing is let's just talk about Fermat's little theorem. Fermat's little theorem stated that if you take any value a that's not zero and raise it to the p minus one mod p, it'll be congruent to one. So this little bit about it, where if I have a mod p, I can raise it to the next power down and it will always return one. Similarly, just a reminder, this actually means that a to the p is always going to also give you a, which is extremely useful if I want to get a. So figuring out anything, I just simply have to raise it to that power. But what did we do when we did not have just one p-value? Well, this was from last time. This was Euler's formula for p and q. So if I have two primes multiplied together where g is their greatest common divisor, then a to the p minus 1 q minus 1 divided by g is congruent to 1 mod pq, as long as the greatest common divisor of a and pq is 1, meaning they're relatively prime. So a is not a multiple of p or q. That's really the fundamental concept here. And if they're both odd primes, then we can guarantee that at least 2 is one of their divisors, so we can apply that. So the nice part, we're going to talk about primes. And besides 2, all primes are odd. All other primes are odd. So we can always divide by 2, which always makes this power smaller. And at least with our, if you stop and think about that, when we do our binary expansion of exponents, that actually makes it much faster to have half the powers. So we can take this and attack it, and these are the ways that we kind of go about this. So all of this, again, how do we solve this? Well, it was about finding values, the inverse of something, mod p minus 1, q minus 1, and so forth. So we had all these different strategies for solving Fermat's little theorem to figure out what do I multiply by if I have a power to get there, and same thing down here. So we still have, but those led us to then ask this, and this again is kind of built on some different ideas, and it was that if you have any two powers that are congruent mod the phi of n, then they're actually equal. A reminder, phi of n is the number of elements in n that are relatively prime to n, which is going to be n minus 1 if n is prime. If n is not prime, then there's actually some different numbers in there and so forth. So this turns out to be extremely valuable because I can just get away with this. So this actually turns out to be what this combined with all of these is what actually gives us this idea. So a couple quick remarks. This proposition, again, is what allows us to solve x to the e mod c, because we just have to find what times e is congruent to 1 mod p minus 1 q minus 1. That's all we have to do. So this proposition was actually the key thing that we're going to use in RSA encryption, and that is why we kind of built on it. Further, so the proposition tells us we could do this, but since it's also congruent to p minus 1 q minus 1 divided by the greatest common divisor of p minus 1 q minus 1, we can actually make that even faster, because now this is going to give us, this right here is much easier to solve than this. It's going to take fewer steps. In addition, this will generate a smaller d. Well, not always, but at least the same, if not smaller. And so this always makes our lives so much easier. And again, because p minus 1, q minus 1, as long as p and q are large primes, they're going to be odd. So p minus 1, q minus 1 will be even numbers and will be okay. All right, so let's get to RSA. Let's walk through how do we actually encrypt all this. So in RSA encryption, the general idea is this. Step one, you have to pick two large primes. When I say large, by the way, I mean like 10 to the 20th power digits. Huge primes. Large does not mean 1,000. It does not mean 1,000,000. It does not mean 1 billion. It blows all of those out of the water. The numbers that we work with are really, really big. You have to know that. So you have to pick two large primes, and generally we want them to be relatively of similar size. Um, so they're not skewed off by one or the other. But that is still a massive problem. We're going to talk about how to find large primes because that's part of this problem is how do you find them? Now, then we're just choose let n be the product of those. And we're going to pick two integers, e and c. And we're going to solve the congruence for what power x, so for what number x does x to the e congruent to c mod n. So we have to figure out what x value. Again, this is almost like, it's not the discrete logarithm, it's almost like a discrete square root. But again, we know how to do this very simply if we know P and Q. And that's the thing. Bob, because he knows P and Q, it's super easy. So this is just like we described in our last class, the last video, how we actually do that. On the other hand, if you don't know the values of P and Q, this is extremely hard. Extremely hard. So we have these situations where we're trying to figure this out. And we have to understand that for Bob, it's really easy because he knows P and Q. For Eve, it's hard because she does not know P and Q. So P and Q become the critical things. So again, these P and Q are what we're going to deal with. So the idea is that solving this x to the e is congruent to c is easy for someone who has extra information, but it's really hard for people who don't have that information. That is the basis of all cryptography. A mathematically hard problem if you have some of the information. If you're missing key pieces of information, it is almost impossible to solve. Not that it is. Truth is, you can still brute force this. It's just will take you a really long time. So let's talk about how you generate what are the keys and how do we generate them? So Bob's first thing is to create two large random primes. Random again simply means he is simply picking two prime numbers that have not not based on another one or something else. And we want them to be not the same. And we want to be roughly the same size, meaning we want their number of digits to be with one or two. So there's a lot of variance in that you can have and still have really, really huge numbers. So now we compute P times Q. That's actually really easy. Computationally, it's considered very easy to do multiplication of two integers, no matter how large they are. Really simple. And we can calculate phi of n, which is P minus 1, Q minus 1. And n is now called our RSA modulus because remember, this is the mod that we're going to have our RSA encryption in. Next, Bob selects a random number e. It's a natural number where e is bigger than 1 and smaller than phi of n. And the greatest common divisor of e and phi of n is 1. Okay, so let's talk about why that's important. So a couple things. Technically, e could be 2 in general, except it would then violate this right here. Because we know that both of these are going to be even numbers, if we're talking about large primes, p and q were odd, so p minus 1 and q minus 1 are both even, which means that phi of n is going to be an even number. So if I pick 2, it's going to violate the greatest common divisor as 1. So 2's off the board. There's possibly other things in there, and we just don't want that to be happening because it'll just cause it actually allows people to brute force even faster. It simply means they're going to have a faster way to get through it. So we want to pick a larger exponent. Now, this exponent is our encryption or enciphering exponent. And we can use the extended Euclidean algorithm to compute e to the d is congruent to 1 mod phi of n, which again, reminder, is p minus 1, q minus 1. I'm just doing this because it's way easier to write down. So D then is because it's the inverse of E, it has to live inside this world. And it cannot be one because E was not one. So it has to be bigger than one, and it cannot be P minus one, Q minus one, because that would be zero actually. So it has to be somewhere inside of those, between those. And we're going to calculate this. Again, this is the extended Euclidean algorithm. If you've not gotten that message that we have to use the extended Euclidean algorithm, I don't know where I missed this semester. This is occurrence. This is the number one algorithm we actually design and use over and over and over again. The other one we use is that binary expansion of exponents. Both of those are the key primary algorithms that we use repeatedly in this encryption process because they are actually the most efficient ways in which we can solve these. By the way, there's multiple extended Euclidean algorithm codes out there. They're not all equally efficient, just fair warning. And I would prefer that you actually write your own. Don't go just Googling something. You all know enough about it. You should be able to build your own code. And even if you get code, remember you have to turn that in if you're using that code for your homework or midpoints. If you don't turn it in, it's just like you didn't turn in your work. All right. So now Bob, he's calculated. So let's go back. He picked P and Q, two large primes. He multiplied them together to get N. He also found the product of P minus one, Q minus one, which we're going to call phi of N. So he's keeping phi of N private. N becomes public. Now he picks an E, it also becomes public. So his big N and his E are public. And he keeps D, P, Q, and phi of N private. So he has four things that he's keeping private and two things he's releasing. And these he's actually going to put on a public database that anyone who wants to contact him can use those. So the key part about this is that, I mean, P and Q you have to keep private because if they're out there, it makes it all obvious. So we have to really, really keep those private. So how do you encrypt things? Well, let's just call M some message where M is less than N. And we'll just say that, so we'll do this and then we'll say we obtain some key. So Alice looks up Bob's key, N and E, and all she does is she takes her message and she raises it to the E power, which gives a C value, a new encrypted value, and she sends C to Bob. So again, she picks some M that was less than N. She didn't pick it. Her message somehow is encrypted into that form. So whether you did the 26, the base 26 expansion into base 10, all those things you could have done ASCII, a lot of other variations of the similar sort of idea. Using all of these, you then encrypt each and every, you can encrypt that. You could have multiple messages, so encrypt them all and send C over to Bob. Now, how does Bob decipher it? Quite simply, he raises the C he gets to the D power. Because remember, EM to the ED is just M. And so when he does this, he's done. He has one step to do, and it's simply raise it to a power. And again, how do you do that? Because we're talking really big powers. It's not actually powers. We're doing the binary expansion and leveraging binary expansion. All right. So let me walk through an actual example. I'm going to not do the actual like extend Euclidean algorithm or the binary expansion of powers just because I don't want this video to take a really long time. And we've already gone over this multiple times. Refer back to past discussions if that's what you want to look at. Instead, I just want to walk you through the general thought process. So if Bob picks, and these are not even considered big, 3,677 and 4,013. And he multiplies them together, he's going to get this N, and phi of N, as a quick reminder, it's just going to be, I got to click on my right thing. That's just going to be 3,676 times 4,012. So that is what our phi of n is. It was just a product of one less than each of these. All right, now Bob selects 5. Again, you can pick whatever value you want. And you can do a lot of different things. Random, maybe I'll bring it up. I'm random really means that everything has equal probability, so everything has a chance. Sometimes people use a random generator. True random number generators are not actually truly random, but that's a whole different discussion point, not for this lecture. So Bob, he picks an E, and all he then has to find is what is E mod 1 of the phi of n. So notice this phi of n becomes right here. And again, the way you solve this is the extended Euclidean algorithm. Run through the extended Euclidean algorithm, we get this. And that is his private key that he's going to keep secret, because that's how he's going to uncrypt everything that comes to him. He also then takes his n value and his 5 and makes them public and says, here, everybody look at them. And by the way, the order in which you put them out there is kind of important. It wouldn't make sense if you did the other way around, because you always do the n first and then the e. But anyways, so Alice obtains Bob's key and wants to send him a message 279257. What that message means, I don't really know. I don't really care. I just picked a number to make this example work. This could be anything because of how you get to this point in time. Were you, again, using ASCII? Did you do base 26? There's a lot of different ways you could have done it. So that has to be understood a little bit. And usually when you're dealing with people, there's some commonalities about some of the things we can use in here. In this certain aspect, 279257, I'm just going to take that and I'm going to raise that. So I should say Alice is going to raise that to the 5th power, because that is Bob's exponent. And she's going to then take that mod this, what's that? 14,755,801. She can take that after she raises her message to the 5th power. She can take it this mod and she'll get 1,028,750. She sends that to Bob. Bob then takes the message, the encrypted message he got. He raises it to his private key, 5899245, and he gets back the original message. And he's done. So again, all of this is why we were practicing all those concepts, because that's the mathematical process by which we get here. And again, if you think these numbers that we are dealing with in this, these are considered tiny numbers. This is not what we play with in the actual real world. We use them way larger because if they're too small, they're easy to brute force. So, couple things, and this is to go back to something I was already saying at the beginning of the video, but I want to emphasize. Bob's public key is n, which is p times q, but he keeps secret the p and q. If Eve knows the value of p minus 1, q minus 1, it's really easy for her to solve x to the e is congruent to c mod n, because that's how we solved it, was because we know p minus 1, q minus 1. So this has to be kept secret. So if we actually just multiplied out p minus 1, q minus 1, you'll notice it's p minus 1, q minus 1 becomes pq minus p minus q plus 1. That's just multiplying it out. Well, pq is n. And this, if I factor out a negative, is minus p plus q plus 1. Wait, so p minus 1, q minus 1, I already know n. If I know p plus q, then I'm done. So the interesting part is if Bob can, Bob is putting out n. So if Eve can figure out what is p plus q without knowing what p is, then it gives her the ability to find that. But the reality is that this is, so if she knows what p plus q is, then she actually knows the p minus 1, q minus 1 product that we're trying to find, because she knows n and she knows 1. So this is not that hard to calculate. So if Eve knows P plus Q and P times Q, which is this is N, and if she knows this, it's easy for her to find that because you just do the quadratic formula on this simple quadratic right here, and you get X minus P. So it's really easy to solve. So in other words, the difficulty of even finding P minus 1, Q minus 1 is actually the same challenge as finding P and Q themselves. And that is the critical part. This is all about the math that going back, it's really, really hard if I give you a big N to factor it out. Prime factorization is so hard. And part of it's also finding the prime numbers in the first place, which we will get to in our next video. Let me know what questions there I have, and good luck.